Light does not possess a point of origin in any conventional sense. Pause and allow that notion to truly settle within your awareness, because this single densely packed assertion possesses the inherent capacity to systematically dismantle virtually every preconception you have ever entertained regarding the nature of the cosmos. I'm not uttering this to evoke a theatrical response, nor am I attempting to fabricate a sensation of awe through carefully chosen rhetoric. I am conveying this to you because it constitutes a direct, unavoidable, mathematically watertight, and empirically corroborated consequence of the most rigorously tested, repeatedly verified, and unquestionably successful theoretical framework in the entirety of humanity's intellectual heritage, the theory of special relativity. This particular theory has been subjected to relentless scrutiny, tested under an immense variety of conditions, and it has emerged triumphant from every single challenge, its predictions validated with extraordinary precision. And what is the core message it delivers? It informs us with absolute clarity and devoid of any ambiguity that from the intrinsic vantage point of light itself, the passage of time is entirely non-existent. Not a minuscule fraction of a heartbeat, not an infinitesimally tiny sliver of a moment, but exactly, definitively, and permanently zero. Let us genuinely contemplate the profound implications embedded within that statement. It signifies that a photon of light did not expend 13.8 billion years traversing the immense, sprawling distances of the cosmos in order to ultimately reach your eye and be detected. From its own inherent frame of reference, it departed from its source and arrived at your retina within the very same instantaneous moment. There was no journey, no period of transit, no ticking of a clock, and consequently no commencement to its existence whatsoever. Hence, when cosmological scientists inform us that the universe possesses an age of 13.8 billion years, they are articulating a time scale that light in its fundamental nature is utterly indifferent to. When you pose the inquiry, what is the age of light? You are formulating a question that the discipline of physics itself declares to be inherently unanswerable in principle. This is because light does not merely lack a commencement, it does not undergo the flow of time at all, and it never has throughout its entire existence. So why then do we continue to cling to the assumption that it must necessarily have one? I am acutely aware of precisely what is coursing through your mind at this very moment. You are most likely thinking that this is merely an intellectually clever play on semantics, a sophisticated manipulation of coordinate systems engineered to produce an aura of profundity. You are probably saying to yourself, all right, fine, that holds true from light's specific perspective, but we are not light. We inhabit a different frame of reference, and that is the one that holds relevance for our ordinary day-to-day experiences. You would be entirely correct in that assessment. However, here is the essential point that must be grasped. That response, while factually accurate, fails to recognize something of colossal significance, something that the majority of science communicators are either reluctant to articulate openly or have not fully reasoned through themselves. That crucial point is this: if we employ time as the yardstick to define the age of the universe, and light exists entirely beyond the boundaries of that temporal structure, then light is not constrained by the universe's age in any manner, form, or fashion. This is not a mere philosophical novelty. It generates a genuine, tangible problem, an issue that confronts not just philosophers musing from their armchairs, but also physicists who are grappling with observational data that stubbornly refuses to conform to the predictions derived from the standard cosmological model. It represents a challenge that is directly facing us, and it warrants our complete and undivided concentration. Prior to delving any deeper into this intellectual labyrinth, I wish to be entirely straightforward regarding the operational philosophy of this exploration. I'm not going to simply cite a celebrated physicist and request that you accept their pronouncements as unassailable truth. I'm not going to dictate to you what the definitive interpretation of the data should be. Instead, my approach is to methodically guide you through the actual experimental findings, the robust mathematical structures that underpin those findings, and the empirically verified physical consequences that emerge from them. Following that, I will leave the derivation of conclusions to you, because this is what constitutes intellectually honest scientific practice. It is not about deferring to authority, it is about adhering to the methodology and observing where it leads us. If at any juncture during this exploration you experience a sensation of frustration, I urge you to embrace that feeling and hold on to it. Frustration is the instinctive reaction that manifests when your existing cognitive framework collides with something objectively real that it simply cannot accommodate. That feeling is not indicative of confusion. Rather, it is your brain actively detecting an inconsistency that your formal education did not equip you with the conceptual tools to resolve. The majority of individuals instinctively retreat from that discomforting feeling, but you are choosing to engage with this material, which suggests that you are cut from a different cloth. Therefore, let us not retreat. Let us proceed deeper into the core of this matter. There are 4 fundamental concepts that you absolutely need to grasp thoroughly before the central thesis can land with the full intellectual force it warrants. I will be completely candid with you. I am intentionally making this exposition rigorous. I am not doing this to exhibit knowledge or to artificially extend the presentation. I am doing it because without these 4 pillars securely anchored in your understanding, what follows will likely appear as abstract philosophy, and it is not philosophy. It is physics. It represents the most foundational physics we possess. So please remain engaged as we construct this conceptual edifice systematically from its very foundations. The very first element you need to acquire a firm grasp of is the actual meaning of a reference frame within the context of physics. I am not referring to the popularized version that you might have encountered in casual conversation. I am speaking of the real, rigorous physical definition. A reference frame is, at its essence, a coordinate system relative to which all measurements are conducted. When you are seated motionless and you observe a car driving past you at 60 miles per hour, that is the velocity of the car as measured in your specific reference frame. However, from the perspective of the driver's frame, you are the one who is moving at 60 miles per hour in the opposing direction. Here is the crucial insight. Both of these measurements are equally valid. Neither one is more fundamentally true or real than the other. This is not a pronouncement of philosophical relativism. It is an established physical fact that has been verified by a multitude of testable consequences. Now this is where the situation becomes exceptionally serious. In 1905, Albert Einstein demonstrated that the laws of physics, including the inviolable and constant speed of light, are identical across every single inertial reference frame. That might present itself as a reasonable and straightforward proposition, but the logical conclusions that can be derived from it are nothing short of mind-altering. If light invariably travels at the same speed irrespective of the frame from which you measure it, then time itself must be the variable that adjusts between those frames. The universe modulates time itself in order to preserve the constancy of the speed of light. The universe does not concern itself with safeguarding your personal perception of time. Its sole preoccupation is the speed of light. You are the variable element, light is the fixed constant. Once you genuinely internalize this radical inversion of perspective, physics ceases to be a mere collection of disparate facts and transforms into a single, cohesive, and profoundly unsettling argument. The second pillar we must establish is the concept of time dilation. I request that you set aside every single analogy you have ever been presented with regarding this phenomenon, because the majority of them are inaccurate in precisely the ways that are most significant for our discussion here. Time dilation is not an illusion. It is not a trick of sensory perception. It is physically and demonstrably real. We know this with absolute certainty because we have measured it empirically. When highly precise atomic clocks are transporting on commercial aircraft flying at ordinary cruising speeds and subsequently return to the ground, they are found to be measurably out of synchronization with identical clocks that remain stationary on the Earth's surface. The discrepancy is extraordinarily small at those velocities, but it is undeniably real, and it conforms to the equations of special relativity with an exceptional degree of accuracy. The GPS satellites that enable your phone's navigation system to function experience time dilation so pronounced that if engineers did not actively compensate for it, your navigation system would accumulate errors of several kilometers on a daily basis. This is not a purely theoretical abstraction. It is a very concrete engineering necessity for contemporary technology. Time dilation is as real and tangible as the force of gravity itself. Now here is what the fundamental equation reveals when you push velocity toward the speed of light. The time experienced by a moving object, which physicists refer to as proper time, becomes progressively smaller and smaller. As the velocity of an object approaches c, the speed of light, its proper time asymptotically approaches zero. At exactly c, proper time equals zero. For a massless particle such as a photon, which is compelled by the laws of physics to travel at precisely c, no proper time elapses between any two events in its trajectory ever. The photon that departed from a star situated 10 billion light-years away and has just now impacted the mirror of your telescope did not undergo a 10 billion-year voyage. It underwent no voyage whatsoever. From its frame of reference, the emission and the detection were simultaneous occurrences. The journey you measured took 10 billion years. The photon measured nothing at all. It is the same event, the same photon, with two completely irreconcilable durations, and both of them are physically correct. This is not a paradox. It is a fundamental characteristic of our universe. The third foundational concept is the spacetime interval. This serves as the crucial bridge that connects what we have just discussed to the broader argument we are progressively constructing. Within the framework of special relativity, there exists a quantity known as the spacetime interval, frequently denoted as ds squared. This quantity elegantly combines space and time into a single unified geometric measurement. For ordinary massive objects traversing the fabric of spacetime, this interval is positive and finite. However, for light, for photons, the spacetime interval is exactly zero. Physicists refer to this as a null geodesic, which describes a path through spacetime that possesses zero length. Consider the profound implications of that fact. Between any 2 points situated on a photon's world line, the spacetime distance is effectively zero. The photon's origin and its destination, regardless of how unimaginably distant they may appear within our reference frame, are geometrically adjacent within the four-dimensional geometry of spacetime. The photon does not travel across the universe in a precise and literal geometric sense. It does not travel at all. It simply connects 2 points that spacetime itself deems to be co-located. Pause and reflect on that realization for a moment, because this is where the majority of discussions on this topic come to an abrupt halt. They present you with the mind-bending fact and then swiftly move on. But the implication of a null geodesic is not merely that light possesses no proper time. It is that light possesses no spacetime extent whatsoever. It exists in the most literal geometric sense outside of what we designate as the universe's temporal timeline. It is a denizen of an altogether different category of reality. The fourth and final foundation is the cosmological timeline itself. According to the standard model of cosmology, known as lambda-CDM, the universe originated in an extraordinarily hot and dense state approximately 13.8 billion years ago. During its earliest epochs, the universe was an opaque fog of plasma. Photons were continually scattering off free electrons and were unable to propagate freely through space. Subsequently, approximately 380,000 years following the Big Bang, the universe had cooled sufficiently for electrons and protons to combine and form neutral hydrogen atoms. The universe became transparent, and the photons were finally liberated. This monumental release is what we observe today as the cosmic microwave background radiation, or the CMB. These ancient photons have been traveling for roughly 13.4 billion years, and we now detect them as a faint, nearly uniform glow of microwave radiation emanating from every direction in the celestial sky. Now this is where the central question becomes utterly unavoidable. We confidently assert that those CMB photons are 13.4 billion years old, yet from the photon's own frame of reference, they are 0 seconds old. They were emitted and detected in the same instantaneous moment. So when we state that the universe is 13.8 billion years old, we are describing a duration that is real and profoundly meaningful for every particle possessing mass, for every clock, and for every observer who experiences the unfolding of time. But light, which is the primary means by which we observe the universe, the very medium through which nearly all of our cosmological data reaches us, exists entirely outside that description. We are employing an ageless messenger to reconstruct the history of a universe that is defined by its age. And no one in your educational journey ever paused to ask whether this creates a fundamental measurement problem. Formulate a prediction before we disclose where this line of reasoning ultimately leads. Ground yourself in what you now understand about null geodesics, proper time, and the cosmic microwave background. Form a prediction within your own mind. If light genuinely possesses no temporal extent, no age, and no duration of existence, does the phrase, the age of the universe, possess a physically rigorous meaning when it is applied to light itself? Ponder this carefully. Do not simply react impulsively. Actually reason through it meticulously, because most individuals, when they initially encounter this idea, tend to gravitate in one of two directions and both miss something critically important. Some will say, yes, of course, age applies to the universe as an entirety, not to individual photons, and those CMB photons are 13.4 billion years old in the only frame that truly matters, ours. Others will argue, no, age is a frame-dependent quantity, and therefore it is entirely meaningless when applied to anything traveling at the speed of light. Commit to one of those positions, because both of those answers are going to appear incomplete in ways that have enormous consequences for how we fundamentally comprehend cosmology. We are going to test your assumptions against the cold, unyielding reality of empirical data. Here is what the data actually reveals to us. The WMAP satellite, and more recently the Planck satellite, have provided us with the most detailed maps of the cosmic microwave background ever constructed. What they discovered was astonishing in its precision. The CMB is almost perfectly uniform across the entire celestial sphere. The temperature variation from one point on the sky to another is less than 1 part in 100,000. This remarkable uniformity gives rise to a significant conundrum known as the horizon problem. The regions of the early universe that emitted the CMB photons we now receive from opposite ends of the sky were, at the time of emission, separated by distances so immense that they could never have been in causal contact with one another. There simply was not sufficient time, even allowing for propagation at the speed of light, for any information to traverse between them and equalize their temperatures. Yet we observe that they exhibit the exact same temperature. The standard response to this puzzle is the theory of inflation, which postulates a period of exponential superluminal expansion during the universe's first infinitesimal fraction of a second. This expansion would have stretched a tiny, causally connected region to the size of the entire observable universe. Inflation represents a compelling and elegant theoretical construct. It beautifully explains the uniformity of the CMB and the observed flatness of the universe. It even generates predictions that subsequent observations have confirmed. But here is what is rarely articulated in the same context. Inflation remains a hypothesis, a highly well-supported hypothesis indeed, but not an established certainty. And here is the point directly relevant to our argument. The horizon problem exists only because we are making a fundamental assumption. We are assuming that causal connection necessitates time. We are assuming that signals require duration to propagate across space. We are assuming that the universe's history is strictly a temporal sequence. All of these assumptions function perfectly for massive particles, but photons are not massive particles. The horizon problem presents itself in a very different light if you take seriously the fact that from a photon's null geodesic, the entire observable universe is, in a sense, geometrically interconnected. I am not definitively asserting that this resolves the horizon problem. What I am asserting is that no one is posing this question with sufficient emphasis, and it is a question that unquestionably merits our complete attention. Now let us discuss what transpired when the James Webb Space Telescope fundamentally altered the conversation in ways that are still propagating shockwaves through the physics community. JWST was specifically engineered to observe further back in time than any previous telescope. Its initial deep field images were breathtakingly beautiful, but what they unveiled was also scientifically disconcerting. Webb detected fully formed, massive galaxies at redshifts corresponding to time less than 700 million years after the Big Bang. These were galaxies that, according to our standard models of structure formation, should not have possessed sufficient time to coalesce into such large-scale structures. The standard model of cosmology dictates that subsequent to the release of the CMB, matter required hundreds of millions of years to slowly aggregate under the influence of gravity. Small structures formed first, followed by larger ones merging and accreting. This is termed hierarchical structure formation. Webb's early galaxies simply do not align with that timeline. They are too large, too structurally organized, and too chemically evolved to have formed within the time the model allocates for their development. The physics community's reaction to this has been precisely what honest scientific practice should look like, not denial or silence, but genuine, tangible uncertainty. New models are being proposed at a brisk pace, modifications to the behavior of dark matter, alternative scenarios for inflation, and the introduction of early dark energy. None of them have definitively resolved the tension. Lying beneath all of those proposed solutions is the same foundational assumption that we can employ light to measure time, and that the duration light has been traveling is a straightforward proxy for the age of the structures it reveals. Webb discovered galaxies that should not yet exist, and every single proposed solution assumes that light's travel time is equivalent to the universe's developmental time. But what if that assumption is precisely where the problem resides? What if the issue is not with the galaxies themselves, but with the yardstick we are employing to measure them? Consider holding three competing interpretations of everything we have established thus far simultaneously in your mind, without forcing them into a single, tidy, and conclusive answer. This is the point at which most science communication fails. It selects the tidiest interpretation, presents it as the consensus, and proceeds onward. We refuse to adopt that approach. Here are the three frameworks that physicists and philosophers of physics genuinely debate when they work through the profound implications of null geodesics and cosmic time. The first interpretation is the relational time view. This position maintains that time is not a background feature of the universe that exists independently of the entities within it. Instead, time is a relationship between physical systems. Specifically, time is defined as what clocks measure, and a clock is any physical system that undergoes a change of state. Light, however, does not undergo internal state changes as it propagates through space. It possesses no internal clock mechanism. Therefore, inquiring about light's experience of time is not a profound question regarding the nature of reality. It is a category error. The question, how old is light, is analogous to asking, what is north of the North Pole? The framework that generates the question simply does not apply to the subject matter. Proponents of this view, who often draw upon the work of physicist Julian Barber and his investigations into timeless physics, would argue that the universe's age is defined by the progression of massive clocks, and light simply is not one of them. The problem with this interpretation, however, is that it fails to explain why light's null geodesic possesses real, tangible geometric consequences for how we measure the structure of spacetime. It addresses the temporal question, but it sidesteps the geometric one, and that sidestep is not a minor oversight. It is precisely where the real tension in physics resides. The second interpretation is the structural realism view. This position contends that what is fundamentally real are not the individual objects of physics, but rather the relationships and underlying structures that mathematics describes. According to this perspective, light's null geodesic is not a limitation or an anomaly to be explained away. It is conveying something profoundly true about the inherent structure of spacetime itself. Specifically, it is indicating that the universe does not possess a single, unified temporal structure in which all physical entities participate equally. Massless fields occupy a fundamentally different geometric role than massive particles. They do not evolve through time. Rather, they connect points across spacetime. The universe's history, as we reconstruct it from light, is therefore not a direct readout of what transpired in a temporal sense. It is a projection of a geometric structure onto a temporal framework that only applies to a portion of what exists. Implication of this view is significant and far-reaching. Our cosmological timeline is real and meaningful for the matter content of the universe, but it may systematically misrepresent the behavior of fields, particularly the electromagnetic fields that we utilize to observe that matter. We are reconstructing the history of the cosmos with a messenger that retains no memory of the journey it undertook. This could account, at least partially, for why Webb's observations continue to surprise us. We are reading a temporal map that was drawn by something that has never inhabited time. The third interpretation is the modified cosmology view. This is where matters become most technically contested, but also most consequential. A growing number of physicists, including those publishing work in peer-reviewed journals, have initiated investigations into whether the concept of a universal age is operationally well-defined at all, not philosophically, but operationally. Meaning, is there a physical procedure one could execute that would yield an unambiguous answer for the age of the universe that does not depend on which type of physical system you are employing as your clock? For massive particles and atomic clocks, the answer is affirmative. For photons, it is demonstrably negative. Some researchers working in this arena, particularly those involved in quantum gravity, approaches such as loop quantum gravity and causal set theory, propose that time itself is an emergent property, not a fundamental one, that at the deepest, most fundamental level of physical description, time does not exist. What we designate as time is what manifests when the underlying quantum gravitational degrees of freedom coarse-grain into the smooth spacetime that we experience in our everyday lives. If time is emergent, then the question of what light experiences is not a question about a special case. It is a window into the pre-emergent, timeless structure of reality itself. This interpretation is the least settled, but it is also the one most consistent with the very frontier of theoretical physics. The strength of this view is that it naturally accommodates both the null geodesic result and the anomalies in large-scale structure formation that Webb has unveiled. The weakness is that it is radically incomplete. We do not possess a working theory of quantum gravity. We have approaches, frameworks, and candidates, but none of them have been empirically confirmed. So this interpretation is honest about what we do not know in ways the other two are not, but it also offers the least traction for generating specific testable predictions at the present moment. You probably disagree with at least one of these three frameworks. Excellent. Disagreeing with one of them means that the instant you experience resistance, you are actively engaging in physics. You are actively posing the question, what would have to be true for this interpretation to be correct? And more importantly, is that something I am willing to accept based on the available evidence? That is not a rhetorical question. That is the actual intellectual labor. Three frameworks, three completely distinct answers to what light's timelessness implies for cosmology. All three are supported by legitimate physics. None is definitively proven. That is not a failure of science. That is what the frontier of human knowledge genuinely resembles, even if most popular accounts will not present you with that unsettling truth. Consider where one might personally stand on this issue while remaining exceptionally precise about what that entails. This is not a final conclusion or a pronouncement of what the science unequivocally states. It is simply one interpretation of what the science renders available, offered so that you can challenge it, refine it, or reject it entirely. That is the only honest manner in which to engage with this material. The null geodesic result does not appear to be a category error. It functions as a signal. When a physical framework returns zero for a measurement, that is typically not a sign that the question is malformed. It is usually a sign that zero is the actual answer, and that this answer carries deep implications we have not fully pursued. What the null geodesic seems to convey is that the universe encompasses two genuinely distinct kinds of physical existence. One that fully participates in time, the matter sector, which includes massive particles, atoms, galaxies, and ourselves, and one that connects points in time without residing within it, the radiation sector, which includes photons and the electromagnetic field. The fact that we construct our entire cosmological picture, our timeline, our distance measurements, our age estimates, and our structure formation models, almost entirely from the second category, while assuming it behaves exactly like the first, appears as a foundational assumption that warrants significantly more scrutiny than it presently receives. Research emanating from groups working on causal set theory, particularly work examining discrete spacetime structure and photon propagation published in Physical Review Letters, suggests that the concept of a photon's age is not merely an interesting philosophical puzzle, but a genuine physical question with testable consequences for how we interpret cosmological data. These investigations indicate that if spacetime is fundamentally discrete at the Planck scale, then the null geodesic of a photon might not be exactly zero, but could acquire a tiny, non-zero effective duration due to the granularity of spacetime itself. This is a prediction that could, in principle, be tested with future observations of high-energy gamma rays from distant astrophysical sources. If such a deviation from zero proper time were detected, it would fundamentally alter our understanding of both light and the nature of time itself. It would mean that light does have a beginning, or at least a measurable duration, but one that is so minuscule that it is effectively zero for all practical purposes, yet non-zero in a way that reveals the underlying quantum structure of space-time. This is the kind of frontier physics that is happening right now, and it is directly relevant to the deepest questions we can ask about our universe.